Welcome to AI Explains.
Today, we're doing a deep dive into what is, well, a truly foundational paper.
It really is. We're talking about the hunt for a missing puzzle piece of the universe, and we're going to try and break it down in a way that, say, a 12-year-old could get it.
That's a great frame for it. We're looking at the definitive paper from the ATOS collaboration at CERN.
Right, and they're using that huge machine, the Large Hadron Collider,
Uh-huh.
the LHC.
Exactly. And the mission wasn't just, to find some new particle. It was about completing the entire rulebook of physics,
The Standard Model.
the Standard Model. Think of it like the master list of ingredients for everything in the universe. It had quarks, electrons, all that stuff. And for 40 years, it worked beautifully.
Almost perfectly.
Almost. But there was one huge glaring problem.
It couldn't explain mass.
Mhm.
The math basically said that all these particles should be massless, just zipping around at the speed of light.
Which they obviously aren't. I mean, we have mass. This desk has mass. So the rule book was missing a page. It was missing the why.
So decades ago, physicists like Peter Higgs came up with this idea.
An incredible idea. They proposed this invisible field that fills the entire universe. And as particles move through it, they drag against it.
Like walking through cosmic molasses.
That's a perfect way to put it. And that resistance, that drag, is what we feel as mass.
Okay, but you can't just say the molasses is there. You have to prove it.
Right. And to prove the field exists, you have to find its particle, the Higgs boson. That's what the LHC was built to do.
So they start smashing protons together at just incredible energies.
7 tera-electron volts in 2011, and then they cranked it up to 8 in 2012. You're basically creating tiny little fireballs with conditions close to the Big Bang.
Just to see if you can shake one of these Higgs particles loose.
Exactly. Now, the thing is, you don't actually see the Higgs boson itself. It's incredibly unstable. It falls apart almost instant.
That's silly. So it's
Yeah.
gone. You're just looking for the fingerprints it leaves behind.
That's it. You're looking at the debris. The paper calls them decay channels, the specific sets of particles it breaks down into.
And they were looking for two main fingerprints.
Two really clean ones. First, where the Higgs turns into 2 particles of light 2 photons.
And the second one.
The second is where it turns into 4 lighter particles, specifically electrons or their heavier cousins, muons.
So they're sifting through the data from millions and millions of these collisions, looking for a little bump.
An excess of events, a spike on a graph that shouldn't be there, all at the same energy level.
And they found it.
They found it. A really clear peak right at a mass of about 126 gigaelectron volts, 126 GeV.
Okay, but in science, seeing a bump isn't enough. You have to be sure it wasn't just a fluke, a random, roll of the dice.
Absolutely. And that's where this 5.9 sigma number comes in.
So let's translate that. What does 5.9 sigma actually mean?
It's a measure of certainty. It means the chance of this result being a total random fluke is about 1 in 1.7 billion.
1 in 1.7 billion, so it's real.
It's as real as it gets in science. That crosses the threshold for a definitive observation. It's a discovery.
So they found a new particle, it's a neutral boson, no electric charge.
And its properties, the way it behaves, its mass, it all fits perfectly with what the Standard Model predicted for the Higgs boson.
The missing page of the rule book was finally found.
It's slotted right in. And it completely changes how you have to think about something as basic as weight.
Right. We think of mass as something an object just has, an intrinsic property.
But it's not. This discovery basically confirms that mass is an interaction, it's a relationship. You only have mass because your particles are constantly interacting with this invisible field that fills all of space.
Which, and this is wild, leaves us with a final thought to chew on.
Go on.
If mass is just an interaction with a field, and we now know that field exists and we've found its particle, could we, one day, learn to alter that interaction?
You mean change the mass of an object?
It's a sci-fi idea, for sure. But the physics doesn't say it's impossible anymore. The door is, I guess, a tiny crack open now.
It's a fascinating prospect. The universe definitely just got a whole lot more interesting.